Welcome! In the previous video, we began discussing time-dependent perturbation theory, and now it's time to actually begin working with it, because so far everything that we saw was exact. We didn't really do any sort of approximation. So now we will take the results that we found, which are precisely these equations right here, these two equations with omega naught being precisely that, and we will apply perturbation theory all the way up to second order just to show you how it is done, but later we will apply this to sinusoidal perturbations, and we will just use first order. Now, why will we focus on sinusoidal perturbations? Well, because we want to apply what we are doing to the case of transitions in atoms, particularly into the hydrogen atom. So for that reason, whenever we are dealing with light, we will have sinusoidal perturbation because of the nature of electromagnetic fields. So for now, we will just do this more mathematical part. We will basically develop the mathematical tools, and then in the next video, we will deal with the physics and apply what we are seeing here. So if we want to apply perturbation theory, right, we will assume that the Hamiltonian that will go into this, right, will be relatively small. Then what we will do is the following. Well, let's assume that we will start at one of our two energy levels, right? We have two states. We have state psi A with probability Ca squared, and we have state psi B with probability Cb squared. So what we will do is we say, okay, so let's say that our system begins in any of the two. Let's say that this is the lower state system. So for example, maybe this is something that represents, for example, n equals 1 and n equals 2, for example, and this will be state A, this will be state B. Of course, we could be representing something else, but this is just so that you know what we are talking about. Our system could be in either one of these states. So let's just say that it begins in state A, right? So we say that Ca at time 0 will be 1, right? So thus, because that is a probability, it will be 100% in that state. And for that reason, of course, Cb will be 0. Okay, so we begin in state 1 or state A, and we know that. Okay, so to zeroth order approximation, so basically no approximation, well, let's put this into this. So to zeroth order, well, nothing happens because at zeroth order there is no perturbation, so there will be no change in time. So Ca as a function of time will be 1, and Cb as a function of time will be 0, right? So to zeroth order, there is no change, and that of course makes sense because, you know, we are at zeroth order, right? We are saying there is no perturbation. That is what zeroth order means. Then we go to first order, and now what we do is that we take this and we plug it in. So for example, Ca as a function of time appears in this expression right there. So to first order, we see that Cb dot would be, well, minus I over h bar, h prime Ba, right, our perturbation, I omega 0 t, and then Ca as a function of time, which we know is 1. So, well, times 1. We don't really have to write it down, but just to make sure that you know that we plugged it in. Then we have Ca dot, but this one is quite simple because Cb is 0, so this is simply 0. Okay. Now let's integrate both of these. So Cb, right, since this is basically dCb dt, right, that's what the dot means. Thus we integrate with respect to time, and we get, so minus I over h bar, that doesn't depend on time. Then we go 0 to t, h prime Ba, Ei omega 0. And now be careful because we are integrating all the way to t, so that we end up with this expression. So we have to use t prime here, right? Just make sure that you don't get it confused. Okay, so just some dummy variable. So this is the expression to first order for Cb. What about Ca? Well, in the case for Ca, we have that dCa dt is equal to 0. Thus, if we integrate, we get Ca, this is equal to some constant, right? CA as a function of time is just some constant, but what we do have here are these initial conditions, right? The initial conditions tell us that CA at 0 has to be 1, right? And since there is no time dependence here, right, CA stays the same at all times, then CA has to be 1, right? This constant is 1, so basically CA as a function of time here is still 1. So as you can see, CA has not changed from here to here. Okay, so that is to first order. Now let's go to second order, for example. So if you wanted to go to second order, maybe let's change colors. So to second order. And maybe let's just make sure, right, this is to first order and this is first order. So let's just put the 1 there to make sure. All right, so to second order, this is the exact same procedure. So we plug in CB and CA into these same equations. So for CB, for example, CB dot, this is minus I over H bar, H prime BA, EI omega 0 T, and then CA, but of course CA is 1, so we don't have to write it down. And now to find CB, we just integrate just as we did before. So this goes from 0 to T, and then we have to change this T to T prime and add dt. Okay, so this is CB. As you can see, to second order, it has not changed, right? You can see that from first to second order, it hasn't changed. Now, what happens with A? Well, CA dot, this is minus I H bar, H prime AB, e to the minus I omega 0 T times CB, but CB is that thing right there. So CB is minus I H bar integral from 0 to T H prime, there we go, BA EI omega 0 T prime dt prime. Okay, so this is CA dot. So now to find CA, well, there's a few things to do. First of all, this minus sign and this minus sign cancel out, but then we have I squared, which gives us another minus sign, so we get minus 1 over H bar squared. All right, and now from this we can see that CA, right, we simply integrate, so CA to second order, this will be, this is minus 1 over H bar squared, and then we integrate from 0. And here we have to be careful because there's a lot of t's, a lot of integrals all the way to t, but they are not the same variable. So we go from 0 all the way to t here. So I'm just going to use a very careful notation here. Then we have H prime AB e to the minus I omega 0 t. So this will be t prime. Then we go into this other integral. So this goes from 0 all the way, and this now goes to t prime. Okay, so that the result from this goes into this integral, right? We are integrating all of this. Thus, we need the result to also be inside of the integral. So our result has to be also the variable of what is inside the outer integral. So 0 to t prime, H prime BA EI omega 0. And now we have to be careful because we used t prime before. So now let's just use t prime prime, dt prime prime, dt prime. And of course, CA would thus simply be 1, which is, this is CA to first order, minus, and then, well, all of this, minus CA to second order, right? So this is what is important. So as you can see, this is the way to go about it. You could go to third order if you want, but as you can see, it does go, it begins to get a bit more complicated, and honestly, we don't really need that precision all the time. First order tends to be good enough. And you can also notice that CA and CB stay the same. They take turns to stay the same, right? So at first, CA stayed the same from 0th to first order, and then CB stayed the same, and CA changed, right? So they are always alternating there. So this is our main result. Our main result is going to be what we found for first order, so what we have colored right here. So this is what we care about. especially what we have here for CB and CA. Now, as I said, our goal is to apply this theory to hydrogen atoms which will be interacting with electromagnetic fields, right? So we will be dealing with Hamiltonians of the form, so let's write it as H prime R comma T, and we will be dealing with perturbations that will be of this form, right? Some radial part times the cosine of omega t, right? With omega, some sort of natural frequency. We will see its meaning very shortly. So in this context, if we want to apply what we just derived, right, these equations right here, mainly this right there and this integral one, then we need to find h prime of BA and h prime of AB. So from here, well, we can see quite easily, we know that h prime of BA, so h prime BA, this is basically psi B, h prime, psi A. So thus, this is psi B, VR cosine omega t psi A. But cosine of omega t has no space dependence, so we can take it out of this inner product, so we can just write it outside, cosine of omega t. And now we don't really know what this is because we don't know exactly what this perturbation is, but we can write this thing right there as V of BA. Okay, and of course, if we have h prime of AB, then this would be V of AB times, of course, cosine of omega t. So that is the notation that we are going to use here. And notice that this is everything that we need to solve what we have here, right? Because what we want to find is we want to study transitions, right? We want to know if we started out, again, I'm getting ahead of myself, but if we started out with something in this lower state, then we want to know, what is the probability if it interacts with an electromagnetic field that it transitions. So for that reason, CB is what we are interested in, right? CB, as a function of time, is what will give us the probability that this lower state will transition into the higher state. That's why we will focus on CB here. So this is minus I over h bar, and then we have the integral from 0 to t, so integral from 0 to t of h prime BA, which we know is V of BA times cosine of omega t e to the I omega 0 t prime dt prime. Now we know that this VBA depends on space coordinates, not on time. So for that reason, we can simply take it out of the integral. We can take it here, VBA. So we only have this integral right here. So we have to solve that. Now, how do we solve this integral? Well, I would suggest that we write cosine as exponentials. So as e to the I omega t prime. Okay, I just now noticed that I didn't use the prime notation before. I hope it wasn't confusing. Plus e to the minus I omega t prime divided by 2, and this multiplies by that. So now let's multiply through quickly. Let's take the 2 outside. So we get minus I VBA divided by 2h bar. And this is integrated from 0 to t. And in here we have e to the I t prime. And then we multiply, and here we have omega plus omega 0. And then we have plus e to the I t prime omega 0 minus omega. So maybe let's write them the same way. So I'm going to write this as omega 0 plus omega. It's the same, but I just like the fact that they have the same form so that it's a little bit easier to process. Okay, so now this integral is very easy because this is simply an exponential, right? It's the integral of the exponential. We know how to solve that. So this is e to the I t prime omega 0 plus omega, and then we have to divide by I omega 0 plus omega, and we evaluate between 0 and t. And the same thing goes for this other one. So omega 0 minus omega divided by I omega 0 minus omega. And we evaluate between 0 and t. So with this, we have minus I VBA over 2h bar. And then, well, let's begin evaluating. So first we get the same exponent, except that there is no t prime, it's simply t now. And then we have minus this thing evaluated at 0, which is e to the 0, which is 1. So we get minus 1. I omega 0 plus omega. And then we have plus, and the same thing, it omega 0 minus omega minus 1 I omega 0 minus omega. Now notice, of course, we can simplify the I. If we multiply it through, they cancel out. Okay, so that's pretty nice. And now this is CB as a function of time. I will get rid of our i's here since we already simplified them. And in principle, this is what we are looking for. This gives us the probability, but it's a bit hard to understand. So what we need to know now is that we will be dealing with situations. Now here we have to notice that since we are going to be applying this to the theory of light, right, we will be dealing in frequencies of about 10 to the 14 hertz. So that means our denominator will be very, very, very large. So in this case, for example, the smallest it could possibly be if you take differing values for omega 0, right, which again depends on the energy of these two states. In case you have forgotten, omega 0 is defined right here, EB minus EA over H bar. So even in the smallest case, this thing right here is going to be of the order 10 to the 14. And if they are basically the same size, then we'll have something of the order 10 to the 14 times 2. And that means that this whole expression will be very small because you are dividing something by a massive number. Right? Since omega will be of the order 10 to the 14, well, then once omega 0 starts to get close to 10 to the 14, we will have something that goes to 0, basically, which means that this entire expression will become very, very large. Now, why is that relevant? Because that means that overall, this expression is always very small, and this expression is also quite small, but larger than this, which means that this term will be the one that dominates. Okay, so that means that this thing right here is negligible when compared to this. And why is that? I mean, if you want to look at it a bit, more rigorously, it's basically because the sum of these two is always going to be much larger, even than the absolute value of the subtraction of them. Okay, so that is why this happens. So that means that we can simply take that to be 0, basically, right? So to h bar, but this is of course because we know that we are going to apply this to the specific case of light. If you are working in some other context, then this is not necessarily true. Okay, this is in principle correct, but let's try to make this look a little bit better to understand it more. So what I suggest here is that we can factor out of here e to the it divided by 2 times everything else. Now, why is that? So let's do it and you will see. So we factor out e to the it omega 0 minus omega divided by 2. That means that what is inside is now also divided by 2, because when they multiply, we will get back what we had before. And then we have minus e to the minus it omega 0 minus omega divided by 2. And all of this is still divided by omega 0 minus omega, of course. Okay, and why is this so important? Because now we have almost a sign, right? Keeping in mind that the sign of x is e to the ix minus e to the minus ix divided by 2I. We have a 2 here, we only need an I. So we can multiply and divide by I, and then we have 2I and our exponents. So we can rewrite this as minus I times VBA, e to the IT, this has not changed, divided by 2, all of this is divided by h bar, and then we have sine of t over 2 omega 0 minus omega, and we divide all of this by omega 0 minus omega. And there we go. This is CB as a function of time. And why is this relevant? Again, because this allows us to find the probability of finding our particle in state B, which is this higher state. Well, now, what is this? Well, if we take the absolute value of this, we get VBA modulus squared. Now, of course, we don't know what that is at this moment. The modulus of the complex exponent is 1, so no need to worry about that. Then we have the sine, so that is going to be sine squared of t over 2 omega 0 minus omega. And then we have omega 0 minus omega squared. So this gives us the probability of finding our particle in state B after having started out in state A, but interacting with, well, we haven't really given it that much, we haven't really given it the exact form of the of an electromagnetic perturbation, but that is what we will apply it to. Now, what is very interesting to note is the form of this, because as you can see, our particle is going to be oscillating back and forth between states A and B, because sine here will go to 0 and to 1, right? It will go all the way to 0, all the way to 1, all the way to 0, all the way to 1. So this is going to be constantly oscillating back and forth. And why is this so interesting? Right, we can do a quick sketch just to understand how this probability works, right? So if we just call this the probability of transition from A to B, we can see how this works with the frequency of the perturbation, right? The driving frequency omega. So what we know is that when omega and omega 0 are very close to each other, this will become very, very large. So that means that we will have some peak, right, at omega 0. So if this is omega, at omega 0 we'll have a peak, and then it will become smaller as we go further away, right? Because this will become larger and larger as omega 0 is either much smaller than omega or much larger than omega, right? So that means that the expression will become larger, but it's still oscillating. So it will continue to oscillate, but just become smaller and smaller and smaller. So that means that the probability of transition is going to be the highest when the frequency of the electromagnetic perturbation is very close to this natural frequency of our system. Now, much of this is still kind of in the air, but in the next video, we will go into the physics, right? So here we just did the derivation. In the next video, all we need to do is solve this part and understand what omega 0 is, and we will be able to go much further. And yeah, I'll see you in the next video. I hope this was useful to you. If it was, please make sure to leave a like on the video, comment and subscribe, and maybe even consider checking out my Patreon. So I'll see you in the next video. Thank you very much for watching.